There we go. Okay, can you do a test now?
Yeah, 1, 2, 3. Testing.
Yes.
Awesome. Okay, this is the last of my lectures in the course. So I do want to throw in, I want to tell you a little bit more about reinforcement learning, although I also want to make sure that we sort of take a little bit of time today and step back and make sure, the most important thing to me over the course of the class, we've introduced a bunch of different algorithms, sort of a whole toolkit of algorithms. And I hope that you've come away with a sense for, if you're faced with a new problem, what algorithm would you turn to? And that is something, of course, that you'll continue to develop as you apply these things more and more. But I want to make sure we take a little bit of time to sort of reflect on the different classes of algorithms and why we use them for different systems. And we can even, we should discuss or we could take time to understand that part of the class. And it's important to me that you walk away with some sense of how everything fits together and not just a random list of random algorithms somehow that we've talked about. Okay, so quick logistics. So project presentations, everybody's seen their randomly generated schedule on Piazza. If you haven't, your assignment, your lecture assignment is on Piazza. I should tell you a quick story. So we've done that sort of randomly generated list for years, but there was one year where I remember we had 21 projects this was a long time ago now, 21 projects to present, project groups, and one person was traveling the week of the final. So they came up to me like weeks in advance and said, I have to present earlier, can I go the week before? And I said, sure, of course, But then I thought, oh. And so I used to do the random scheduling thing live in class. And I said, this was on the Tuesday before, right? I said basically, okay, there's 21 projects, so it makes sense to do 10, 10, and 1. So one of you will end up having to present, on Thursday, right? And then I said, we're going to do this randomized algorithm, and as it goes down, and I made it worse. I always started it from the end, so it'd be like the Thursday final presentation. It would going backwards towards the beginning, and I even put like pause statements in my MATLAB code to make it more and more suspenseful. And that one year where the one person was sitting there knowing that it was him, and it was no big deal. But everybody else was like, oh my God! They started making deals with each other across the, So I regret that we didn't get to so much drama today, but I hope that the randomized algorithm is still useful. We're going to make the projects work. Let's start, the wall clock, I always start at 2:35, but let's start at 2:30 sharp. I mean, we're cutting it close and the room is available. So let's start at 2:30 sharp. Greg and Pete are already figuring out how to have dual projectors, and so instantaneous transitions, and they're going to help you through all the logistics of it and everything. And Greg sent some of the instructions if you have any questions, but you don't have to tell people the algorithms that we've already talked about in class. Tell us the system you picked, the problem you tried to pick, show us your results, and in particular, I want to hear anything that surprised you. I thought sums of squares was just going to work and it just didn't, or any surprising results. Those are the real gems that everybody's. I mean, seeing what did work is awesome. Seeing something that you learned along the way, you can communicate that quickly in 3 minutes, and those are great to include. Of course, you can, since the final project is due later, it's okay to say there's a couple things that aren't working yet, or don't feel like you have to have the final result. Tell us where you're at. Of course, the further the more exciting it is, but we understand that this is before the final write-up is due. Questions about that? Okay, so let's do a little bit more reinforcement learning. So last time we did model-free policy search. And really, we focused on model-free policy gradient methods. Right? So the idea was that the idea of the policy gradient is I have some controller in the simplest form. If it's a deterministic controller, then we could parameterize it as some function u is pi of x, and that's got some parameters that control it, whether those are the gains of a linear feedback or the weights of a deep neural network. This is just some parameter vector alpha, right? And for the policy, for the reinforced derivation, we thought of this as a probabilistic policy that depended on alpha that gave you some distribution over u that was conditioned on x. Right? That was just the probabilistic interpretation of it, because we were going to use that log probability trick to take the update. And the ideas there were that we can directly search in the parameter vector alpha and watch our performance improve, right? And we can try to estimate the gradient, the direction which we want to make that improve by trial and error search over the parameters alpha, right? In the case where the evaluations are noisy, right, then it becomes a stochastic gradient. Well, always it becomes a stochastic gradient descent. And in the case where it's noisy, you're often going to go uphill as well as going downhill, and you only just hope that in general we're going to go, in expectation, we're going to go down the hill. And the major plight of these algorithms is that they are typically not very sample efficient. The estimate of the gradient has high variance, so we really spend a lot of time going in all kinds of directions, and only on average do we actually go down the gradient. Okay. There are sort of two ideas connected there. One of them is the idea that you can just search directly in the parameter alpha. You could do that even if you had a model of the system, right? And you could use gradients that you could calculate with the trajectory optimization type gradients, for instance, to optimize alpha. And that, I think, can make sense for systems where, for instance, you think there's a simple representation of the policy, but maybe no simple Lyapunov function or value function or cost to go function. Those direct policy search algorithms can make sense. For my vote, doing it with trial and error instead of true gradients, that sort of only makes sense if you don't have any chance of getting a model. I think in many cases, people use them too quickly, and even approximate models would have been much more efficient than trial and error learning. Okay, so the fluid dynamics was an example where I said, right, the model that we have for that is not useful, so we're going to go ahead and do trial and error learning. And even that one, we probably could have come up with an approximate model, but so you use them wisely. But there is a very interesting idea about the model-free policy gradient that I felt like I should have emphasized before, right? So the performance of those algorithms in terms of the number of samples required to sort of optimize a policy, it scales with the number of pieces of noise that you introduce into the system. Number of noise variables, that's kind of a weird thing to say. Noisy samples or something, but on each step. So when we did the pure weight perturbation, it's like the number of parameters in your system. The length of the vector alpha is what determined it. In the reinforce update, it was slightly different. If we could have a deterministic policy, right? We could say that U was some deterministic policy plus some noisy vector V, or W, let's say. And this was deterministic, this was noise. So if I do this, then the number of noise elements that I'm sort of adding to the system is just the number of control inputs. And then I could use gradient descent to take the change that I've made in W and make it more likely using alpha. right? That was the reinforce idea. So you can decide where to add the noise into the system. You could search directly in alpha, or you could search in the output. This was the reinforce idea. And this is going to be more efficient. I did type up all the lecture notes after the lecture on Tuesday, and I included a little analysis using the signal-to-noise ratio, which shows that the signal-to-noise ratio of your gradient estimate scales with the dimension of your noise that you input in all the simple cases. Okay, so if you have a lot of parameters alpha, you've got a deep neural network or something, but you only have a few control. If the vector u is small, then it makes a lot more sense to add noise to the output of the neural network, and then the trial and error learning now says, I'd like to make that output more likely, but I know the gradients of the neural network, so I can change alpha to make that more likely. Okay, is that clear? Yeah.
Can you give an example where you think that the policy is easily parameterized, but the output function is not?
Picking up a coffee cup, right? So any of these systems that we've talked about with contact, we've struggled to find simple Lyapunov functions, but I think guarded moves, are pretty robust and pretty simple. When I watch the Boston Dynamics videos, I think the same thing. I think they've found pretty simple to write controllers that are, state machines or whatever that work pretty well, but the cost to go is hard. I think the Rayburn Hopper is a good example. I think even the energy shaping controller on the simple pendulum, that's a pretty simple controller, but writing the cost to go in the original coordinates is actually kind of gross. Okay, so it's really interesting to think that the performance now scales with the number of noise variables. It is relatively independent of the complexity of the dynamics, right? So the
more noise variables increases the variance of the gradient estimate.
That's right. So it would take more Monte Carlo samples to efficiently estimate the direction of the gradient. Of course, there's another question about just how far do you have to go downhill on your gradient, but this is a pretty good correlation with sort of learning performance. So the fluid dynamics experiment, right, was a ridiculously complicated dynamical system. It took me a long time to simulate, but the performance of the learning algorithm it was invariant to the complexity of the fluid dynamics. I could have put more fluid dynamics in somehow if I put more boundary conditions or something like this. It would have been even more complicated to simulate, but the learning would have been agnostic. So that is a very nice feature of the algorithm, right? And it means that they pay off in cases where you have simple parameterizations. If you have a handful of outputs or something like this, or you can somehow, the place of control exploration is small, even though the dynamics is rich, then these algorithms can pay off. Okay? But they're still throwing out a lot of the structure. All the structured sort of optimization we've been talking about with finding convexity or doing sums of squares or doing, even in the constrained optimization is sort of gone. We don't, so they pay a price for this, the scaling is good almost because it's naive, right? The approach is naive. So today there's a related set of tools that are going to make that a little bit better, right? We're going to now try to estimate the value, j of x. We'd like to estimate ultimately j star of x, the optimal cost to go, but we'll start by even just making sure we can estimate, given some current policy, the expected cost to go, and I'll put hats on whenever I'm talking about estimates. There's a related function that I'll try to make sure you understand that you often also try to estimate, which is the Q function. can learn it for a particular policy or for the optimal policy. Okay, and really, given an uncertain system, there's sort of, there's a bunch of things you could try to learn. You could try to learn the dynamics, whether you model it as deterministic or stochastic. That's one thing. You could try to learn the policy directly. That's what we talked about last time. Or you can try to learn the cost to go directly, right? And we'll find out that there's really nice ways to mix and match and use multiple of these approaches together. And I'll also talk specifically about learning pi and j together with actor-critic methods. Okay. All right. So let's think about how do I estimate even the cost to go j pi. And that step is typically called policy evaluation. Okay, and we actually mentioned it before when we were talking about Lyapunov functions. The simplest way to think about that is in a finite or a discrete Markov decision process. Right, if I have a graph where I have action 1, action 2, I'll even make discrete actions here, action 2, right, and I've got some transition probabilities and the like, right, where my cost is some long-term cost, and I'll do the discounted version just so we don't have to, since we aren't being precise, I'll just make sure that it's well behaved in the long term, right? This often makes sure that j as n goes to infinity doesn't go to helps avoid j going to infinity, right? Gamma is always between 0 and 1. Okay, so if I'm given a policy or some probability distribution, then how do I do policy evaluation? Well, in the particular case of a Markov chain or a Markov decision process, it's easy. Once I have the policy, it becomes a Markov chain. If I have a probability distribution, it's still trivial. And you use the recursion. J pi of s is the expected value of GSA. In general, it could be random if A is described as a policy, plus gamma times the expected value of J pi at the next S. J is not J as a function of S is just a number. It's not a random variable. But since S prime has some distribution, there's an expected value of this, given the dynamics, right? But this thing is something we can just evaluate for S, understanding the probability distribution here. So that thing is really just like a vector G. If I write this as a vector in our vector notation, because it's finite horizon. And the uncertainty here is all in the transition probabilities, which can be captured in our transition probability matrix like we did before. This is hopefully just a reminder. Okay, times our vector J. So policy evaluation is actually just a least squares problem. It's a linear equation solve, right? I minus gamma t inverse g hat. So that's a reminder of policy evaluation being sort of easy if you know the transition probabilities. Okay? We even talked about this in the Lyapunov case of saying we want to maybe match this dynamics but add an extra constraint that j goes downhill, and then the solution became a linear program. Do you remember that conversation? Okay. So the game today is now, let's say you don't know t, or you don't know the distribution over, this I guess you will know, but let's say you don't know t. How do you then do policy evaluation? How do you do policy evaluation from trial and error? Okay, and the first idea is idea number 1. Let's use Monte Carlo analysis. Right? If I'm in a particular state, I can estimate j hat of pi from any given SI by just running a lot of simulations, right? It approximately equals 1 over n, sum of the long-term cost, right? To some big enough n, but sorry, let me. Idea number 2, though, is to leverage this recursive structure, right? This is not very sample efficient. It might take a lot of n to get a good estimate of j, right? What if we could use that same sort of observation and the recursive form and additive cost form of the cost function to then bootstrap, people call this bootstrapping in reinforcement learning, to somehow maybe improve the efficiency of my reinforcement learning algorithm by saying that j pi of SI is my real data for one step plus the estimate of my cost on the, in the future. Where these are now sample points. Okay, in the case of a finite Markov decision process, this is a vector, and you can just calculate this up and solve a least squares problem to find now the vector that makes the one-step data match the longer-term observation in a least squares sense. If I'm using a function approximator here, whether it's a linear function approximator like we talked about before, or a deep neural network, then again, this becomes now just a training. Just becomes your L2 loss. Like you make this is now a supervised learning problem to say I'd like my my cost to equal my one-step data plus my future cost discounted. Right? So it's a simple supervised learning problem.
Is SI Sj, or are they independent?
Sj is, so another way I could have written, I wrote it like that because of this notation, but let's say if I'm following a particular sample path, I could call this S at n, and this is S at n plus 1. So if I get some samples along the trajectory, right, this is the cost that I got at one step plus the cost I got at the next step. I'm going to accumulate a lot of data like that by running lots of random samples, and I'd like to try to make my function approximator describe the, be consistent about the long-term cost. Yeah? The goal of setting these two things together and the error that you have in matching in that approximation is a famous term. It's called the temporal difference error, right? So this term here is called the temporal difference error. Or TD. Okay. And there's a whole grab bag of algorithms that use this that attempt to minimize this temporal difference error, right? So LSTD, least squares temporal difference learning, tries to collect a lot of data and then solve the least squares problem by, for instance, just doing supervised learning. But there are also online versions of this that on every update, as your robot is moving, it tries to make sort of a low-pass filter of the least squares solution and incrementally updates J hat in order to try to minimize this on each step, okay? And that's called temporal difference learning. TD and TD lambda is the general form of temporal difference learning. You could think of that as a low-pass filter on the least squares solution. It's not quite that. There's an extra term that pops in. You think, why does that even work? It's not doing least squares, but this was sort of the intuition behind it, and it works surprisingly well. Okay. There's actually a great book by Dmitry Bertsikis and John Tsitsiklis called Neurodynamic Programming. It was written 20 years ago now, right? And the book is great, but the preface is fantastic. The preface basically says, we've been studying dynamic programming for years. There's a bunch of these people that are talking about reinforcement learning, and at first blush, their algorithms appear ad hoc and unjustified and unprincipled, but they appear to work well in many situations. So we thought we would, do some analysis and see if there's anything to it. After spending some time, we basically think that their methods are ad hoc and unprincipled, but they do in fact work, and we'll tell you what we know about it. And I don't know, just somehow the deadpan way that they wrote this, it's worth reading. Neural dynamic programming, but there are a bunch of tricks in the sort of temporal difference learning world that you feel like shouldn't work, but somehow work really well.
So it seems like for estimate for approach 1, it's pretty clear that that's going to converge to the true J pi and probability or something. It's pretty. You can probably prove an easy theorem. Is it clear that solving this least square solution also gives you some convergence properties?
The theorems say that for linear function approximators, they will, TD lambda, which is a slightly more complicated version than this, does actually converge for linear function approximators. I don't believe anybody has the more general result. Okay, so So there's sort of two approaches, and so the full version of temporal difference learning actually has an elegant way to combine a few rollouts. Like I could have done this in any number. I could combine Monte Carlo with the temporal difference learning in any amount of right? So I could have said, this is my one-step cost plus the cost to go on the next step, on step 2. I could have taken the one-step cost from data, the two-step cost from data, and then use the third step to do using my cost to go estimate. I could have done it with any number of steps from data and then my long-term cost. Okay, so you can sort of walk between Monte Carlo and the approximate cost to go, the recursion here. And TD lambda tries to walk that line where the lambda parameter, which is between 0 and 1, gives you either the short horizon version or the longer horizon version. Now, many of you know Alphago was a success story of temporal difference learning and the like. It was very interesting. So in Alphago, they did learn an approximate value function in a deep neural network that took the Go configurations as an input image and tried to predict the cost, the chance of winning, right? It was just 0 or 1 whether they win or lose. Okay, and they did a really nice. If you haven't read the Nature paper, you should. It's short and very convincing and very clear. But they actually found that even at runtime, when they're evaluating their policy, they would combine rollouts to understand, to basically simulate a handful of steps forward, and their cost to go that they learned in a deep network. And they have some great analysis at the end, which said that if they just use their neural network as their approximation of the cost to go, they perform better than everybody else still, but not nearly as well as themselves when they used Monte Carlo rollouts online plus the cost to go. So the Monte Carlo approach to online simulation would be, I have a probabilistic policy, the opponent has a probabilistic policy, I'm going to just, I'm going to think ahead for as many steps as I have cores to think about, right? And then use the value function at the end and decide my best action. They had a version which ran on one machine with 48 cores, and they also had one that ran on the cloud, and they used the cloud in the biggest competitions, but they used the single machine for all their analysis, really. And there's a big idea there, which is that the approximate value function gets you somewhere. You can compensate for the representational errors, really, in your approximate value function by combining some Monte Carlo on the fly. That's a really sort of important idea in RL.
Is that just because gamma? Does that work even when gamma is equal to 1? Sort of? Like, is it just the fact that if you go out 10 steps, are you just raising your discount factor to the 10th, and so errors just get reduced, or is something deeper going on?
So I should be careful that when gamma equals 1, it actually merges short-term and long-term still. It's not quite only do Monte Carlo at 1. It's more subtle than that. So the idea is that the rollouts are more precise, but they're still a sample. You can only afford to do some of them, right? And the long-term cost is, captures a summary of things that you couldn't possibly capture with a finite number of samples. So somehow combining the two, the AlphaGo story was even more complicated because for rollouts they used a player that they had trained that was a smaller neural network, so they could roll out faster. Yeah. So there's some subtlety there still, but they still analyzed and showed that that combining the two was by far the best. Okay, so there's a problem though. Of course, we talked about, we've always used the cost to go as oh, I'm sorry.
Wait, so the Monte Carlo approach makes sense for like getting some JPI, but when you're doing bootstrapping, how do you find, how do you do that? So you can get your cost, that's fine, but if you have an initialized JPI, then how do you do the like forward states?
this is almost exactly what we did in dynamic programming, right, in value iteration. And it was surprising but true that, that even if you just set j pi to 0, then what happens? Well, on the first sort of round of data, j becomes g, the one-step cost, and then as time evolves, you'll get more and more of the longer-term cost. So in the simple case of value iteration, we actually had convergence. We understood that to be a contraction mapping, and we know it was going to converge. The data story is more complicated, but it's analogous. There's some subtlety that I think that people play when using this in practice. So starting j to be 0 everywhere gives you a nice intuitive understanding that it's going to learn farther and farther into the future. Sometimes you can also start j to be very high, very optimistic, let's say. Sorry, I flipped my reward versus cost. You could make it very optimistic, saying that my cost is going to be low, for instance, in many other states. And that's a trick that people use to encourage exploration. So if I've got parts of my state space that I haven't visited yet, then I'll assume good things happen there, and that sort of encourages my controller to go out and explore those areas. And then that might be bad for a humanoid robot that's walking near cliffs, but it's fairly benign in Go. Okay, there's one more problem here, which is that we've always said that having the cost to go was tantamount to having your optimal controller, right? So once we had j, we just evaluate its gradient, and we know that we know how to go downhill. But that assumes you have a model, right? So how did we, in the past, in order to get the optimal controller out of the cost to go, we needed to have the dynamics, subtly, right? But pi star from S, if I stay in the discrete time but discrete state, was the argmin over A of my one-step cost plus my value function. But this S prime is really my after one step of the dynamics. In continuous time, continuous state, that just becomes a gradient. I had in my equation, I had partial j, partial x, partial f, times f, right? In both cases, in order to figure out what direction to go down, what action to take, I try to find the steepest descent of my cost to go, but to figure out the steepest descent of my cost to go, I need to know the consequences of my actions. I need to know my model. So so suddenly now, you can't only learn the cost to go and then be able to make decisions. So what to do about that? So the thing you can do is you learn something slightly different, which is a Q function, QSA, right, or X if it's continuous time, is my one-step cost plus my cost. Where this is now j pi. And similarly, Q star SA is the min over A GSA. I'm sorry, which are A?
The bottom function. This one.
It just no min. Is it just J star?
It's J. Yeah, I'm sorry. Thank you. It's really just this is what captures that, right? That captured the min. Yeah, you're right. Thank you. Okay, so you learn something slightly bigger than the cost to go. You learn what is the cost to go of taking action A for one step and then following the policy, right? It's almost the same function. All the same temporal difference learning ideas can be used to learn this, but it gives you the ability to take an action, to infer the optimal action from your acquired function. There's also another cool thing that happens when you learn Q instead of J, is you can do something called off-policy learning, right? There's also this idea which is the idea that I could actually learn about policy 2 while executing policy 1. Because I'm building up a table of what would have happened if I had taken some action, and it somehow separates out the learning from exactly what the policy is. So there's this cool idea of learning off policy, which is really good, for instance, if you want to learn about the optimal policy while taking actions based on something that's doing more exploration, for instance. This becomes a very powerful idea. And I feel bad not going into more details on these things, but I don't want to get, there's a lot to say that I don't have time for. So those are sort of the big ideas. The big idea is you can learn a cost function from trial and error, a cost to go function. It's not quite enough to make actions, so you learn something just a little bit different from the cost to go, which is this Q function. And that's enough now you can take actions from it. And it's also got some cool ideas of learning about a controller that you're not actually executing. But what I want to bring back is that is maybe even the biggest idea here is when these algorithms make sense and what do they do, right? So the policy gradient algorithms had a remarkable property that they didn't actually require you to know the state. The way I wrote it before implied it, but let's just think about the output feedback problem here. So in policy gradient, the way I wrote it last time, it was, I said, let's say you're looking for some function like this, okay? And I have a dynamical system like this. But actually, everything I talked about last time could have worked if I had done something slightly different. If I defined some output, some sensor measurements, for instance, and I wrote my policy as a function of the outputs, not a function of the state, then all of the math we talked about last time still worked. Okay? So what does that mean? So I'm a robot trying to manipulate a towel. I can write down controllers which go from the image, my pixels, right to my torques, if I would like, right? If I just want to take the image of that the robot is currently seeing of the towel, I don't actually have to infer the state, estimate the state of the towel. I don't even have to understand how big that state space is in order to write a controller that just maps from my current image to my torques, okay? By trial and error learning, where I'm just changing my controller a little bit, trying the experiment again, changing the controller a little bit, I could optimize that output feedback controller directly. It's powerful in the sense that it doesn't need to know the state. That's a big idea. I mean, again, it's powerful in its naivety, right? So it's kind of like, it's because it's not leveraging the structure of state space that it is agnostic, okay? But that's a big idea. Somehow the value methods I've talked about real quickly They are good in the sense that you didn't have to know the dynamics of your model F. You could get that through trial and error learning, but somehow it does have the notion of state space baked in. So these, I at least have to know how big the state space is somehow in order to write my method, write my value function, and have that expect that to converge. But there's an interesting way to put these two together, which is a different way to sort of use an approximate value function, which is called actor critic, okay? And it uses them, it does policy gradient plus value methods. And maybe it'll get us back to the idea of being able to write controllers without knowing the state space. Okay? So there's a bunch of actor critic methods out there also, but I can actually connect it directly to the one we spent some time, the policy gradient method we spent some time analyzing last time. Okay, so remember last time I said the simplest version of the weight perturbation, sort of weight perturbation update was to take a step where I said, I'm going to take g of x plus my beta, you know, this is let's say alpha plus beta minus g of alpha times it by my beta. And we understood that. And then I wrote a simpler one, which was g of alpha plus beta minus the baseline, and said that one still worked in expectation. And in fact, even if the baseline was 0, that still worked in expectation. Right? You'd love to be able to do 2 evaluations, but in practice, you can't, for a stochastic function, you can't expect some small difference, you know, you can't evaluate the function twice reliably. So the simplest sort of actor-critic algorithm, and one of the most popular, really, is to use the baseline as my I'll use j hat as my baseline, okay? Why does that seem like a good idea? So if I'm crossing my notation a little bit here. I'm trying to keep the g hat of alpha, which in the trajectory case looks like j hat pi of, let's say, x. Okay, so this baseline here is a candidate for sticking in the cost to go approximation. Why is that a good idea, right? So what I'd like to do is add a little noise to my system, to my parameters, beta, okay? I get a noisy measurement by doing an experiment with my perturbed parameters, and I'd like to know, was that a good experiment or a bad experiment? Comparing it against the expected value of the expected performance j under the original parameters gives me a sort of a reduced variance update of how good this cost difference is. Okay, so actor critic methods allow you to somehow stick a cost to go estimate here and reduce the variance of policy gradient. And the magical thing here is that our results on the policy gradient suggested that we will move in the direction of the expected value regardless of what b is, as long as it's uncorrelated with beta. So I can stick in the true value function. That would be great if I could get the true cost to go function. But I can also stick in a pretty noisy approximation of it and still hope to do better than if I just set it to 0. So there's room here for even having very approximate cost to goes, which may work even on subsets of the true state. So you could imagine your robot looking at the towel still getting some function, learning some function of, from the image, I could learn how, the cost I'd expect to get. It's not guaranteed to converge in ways that the true cost to go are. But you can imagine having some function that you've learned, which tells me every time I've seen this picture, this sensor output, I've obtained the following rewards under executing that policy. So you can get away with pretty approximate estimates of the value function. And that can get you, again, away from having to, it gives you some of the advantages of using cost-to-go estimates and model-free value methods without the constraint of having to understand the state space of the system. Okay? So I actually want to take you back a few years. I did my PhD thesis on this, and it warms my heart, makes me laugh. I don't know, something that actually the algorithms that I used back then are still the ones people are using today. They're just deeper now. So I actually pulled up my slides from my job talk at MIT from way back, and maybe it'll help you. It'll help me tell the story a little bit. So let's just do that real quick. So even back then, I was trying to get analytical approximations to the optimal control, for something like Asimo at the time. Asimo was the king, right? But I've always believed that learning makes sense, for online adaptation to changes in the environment and things like that, right? And so my thesis was about trying to demonstrate fast online control optimization for a biped, okay? Here we go. So at the time, there was people doing, RC helicopters, which was iterative LQG, basically, or LQR, to do inverted helicopter flight. These were sort of the success stories of reinforcement learning. They were doing open loop trajectory optimization for IBO to play soccer. There was a cool robot from University of New Hampshire that, I'm not sure why that's not playing, actually.
If you go back and press the play button after you hover over the video, you see it?
Yeah, I do see it, but I see it smaller over here. Yeah. This was a learning biped from 1994 at the University of New Hampshire. It was awesome. Learning how to walk, okay. It took a long time to learn how to walk. That guy was very patient, but that was an early success story for reinforcement learning, okay. So, all these problems that we've been talking about here were problems then: large continuous state and action spaces, complex dynamics, difficult to model well, limited number of trials on the real robot, collisions stink, delayed reward, okay. So, all right, I built a simple robot, right? So I tried to build a robot to simplify the learning. Instead of working on Asimo, I built that thing. Called it Toddler because it toddled, and because that made everybody like it instead of talk about how simple it was. And I was talking about rimless wheels back at the time too. Toddler is basically a simple version of the passive walker that walks down that complicated ramp. Okay, so you remember the Collins. You remember this robot, right? This is awesome. It completely inspired me as a grad student, and I tried to build the simplest version of that. But I didn't have a lot of funding at the time. I worked with a neuroscientist, and he was nice enough to let me have a machine shop down the hall. And the way I convinced him was that he started spending a lot of money on microscopes for neural recordings. And one day I was like, you know what? For the amount you just paid on that lens, for that one lens of that microscope, I could buy a CNC mill, and it was a small CNC mill, whatever. And he finally told me I could, and I went down the hall and started building robots. But I didn't have enough money for a ramp, so that's a CD rack and a piece of wood. I had to use some rubber, so my ramp got the corner was cut out of the ramp, right? So this was pretty low budget science, if you will. This was my passive walker. Which actually is one of the simplest 3D passive walkers you can imagine. It's basically like the toys you buy with a string. Okay? worked pretty well.
How did you design that?
That was, I mean, I optimized the curve. I wrote a MATLAB program to spit out G code and send out to the CNC mill to cut those curves out. I had sagittal and frontal models to understand the curvature and its relation to the gate.
And was it just some big nonlinear optimization to decide what the curve was, or?
It was I did a, you know,
Or just parameter sweeps?
I did roughly parameter sweeps, yeah. I tried to make the frequency of the natural frequency in this direction match the natural frequency in this direction, you know. Okay, so a toddler is basically that robot with a few extra bits. The hip joint is still passive, okay? Added actuators to the ankles, okay? But they control the pitch and roll of the ankles. But they had the property that when the motor was just holding its position, which was basically sending 0 commands to the hobby servos, then it walked just like the original passive dynamic walker. Its leg was hollow, filled with tilt sensors, rate gyros. There's potentiometer at the hip. The arms were it's sort of clever. You can mechanically link them to the opposite leg, and I put all the mass in the batteries on the arms, because if you have no arms and you swing your leg forward, then you have a tendency to twist. Okay, so you put a mechanical linkage, which is what that shield thing looking is. It's a mechanical linkage to connect those two links, and then you tend to not rotate as you walk forward. Okay, so that worked pretty well. In total, 9 degrees of freedom, 4 actuators. Okay, the dynamics are, I used H back then, but otherwise pretty much the same, right? And the key idea was that on a ramp, it's a stable walking gait with no control. And on the flat, it acted like a damped oscillator that just ran, you know, so pretty benign dynamics that would run out of energy and stand still. And the goal was to find a controller to stabilize the nominal limit cycle on any slope. This is with the actuators doing no work. Treadmill that I eventually purchased. It took a long time, and somehow they thought I was going to exercise when purchasing all this, so that was really, really hard to convince them that it was not speed. I had to leave that on a table at all times. I was not allowed to put it on the floor because I might exercise. And this robot would walk all day long. He was maddening, you know, I was running my pieces all day long. Okay, so back then we weren't deep yet, but we did linear function approximation with nonlinear basis functions. And there was actually a big idea back then that seems to be lost sort of right now, which was it mattered a lot to me to have very local features. So it was important that those basis functions had a small basin of sort of region of support in the state space, because this was an online learning exercise. The robot would walk around and learn, and then it would walk somewhere else and learn. And it was important that as it was spending time in one part of state space, it wasn't forgetting what it learned in a different part of state space. So it was common knowledge back in the day that you'd want that you were much better off with local function approximators. And people talked about tile coatings and other very local function approximators. And so I think certainly convolutional networks are capable of doing that, but I don't know if that's strictly imposed by the structure, or if you know, it's interesting to see that there hasn't been a big discussion as much lately. Okay, so at the beginning of every footstep, every time that robot took a step, it did a small random change to the policy parameters. It would take one step, and at the end of that step, it would evaluate its change in walking performance and make a permanent change to W based on those results. So it was doing policy gradient type things, but on every footstep. Okay, so each test estimated the policy gradient. It performed online stochastic gradient descent. And the big questions maybe were, what were the right cost functions for walking, and how do you get fast provable convergence despite the noisy gradient estimates? Van der Pol oscillator, right? Return map analysis. Okay, so the return map, you know, I did this curve on lecture 3 or something here, right? The Van der Pol oscillator return map looks like that. You can do everything you guys understand about linearization and stability analysis. But the key idea was that the optimal return map, if I was trying to control the Van der Pol oscillator, would be maybe the deadbeat controller. Right? So if I really had my walking controller working well, and I'm trying to stabilize a nominal limit cycle, then on a single step, I'd always return to the nominal limit cycle. Okay? That was the key behind the objective. So the cost function I used was the distance between the current estimated return map return and the optimal, the deadbeat controller. Okay, that was the cost function. All right, so the goal was to find this long-term average, average cost. Everything else is things you know. Find W to minimize that infinite horizon cost, where the cost function was this simple function, where the location of the limit cycle was taken from the downhill walking of the robot. All right, so on each footstep, add mean zero Gaussian random noise directly to the parameters, okay, which was fine for me because I had a local function approximator. The difference in doing it for the outputs versus doing it for the parameters was negligible in my case. At the nth step, I made this gradient update, which is almost exactly the weight perturbation update. Okay, and in batch, I know that performs stochastic gradient descent. This is what we talked about last time. Okay, and here's the picture I used to explain it back then, right? Noisy gradient descent. Okay, but I also learned a value function. V is called the value cost to go function, and I stuck it in exactly like I just proposed here as a baseline in the policy gradient algorithm. It didn't change the mean of the batch update, okay, but it can dramatically reduce the variance. Now, the interesting thing is, even though the state space of the robot was large, like I said, you can actually learn a very approximate value function and still have it improve the variance of the controller. So I learned a very low-dimensional value function and still reaped the rewards of decreased variance. Okay, so the value function was a function of only one variable, actually. That was what learned fastest. And the policy was only a function in this plane. I didn't worry about optimizing this plane. Okay, I was just trying to stabilize the limit cycle, letting the dynamics then play out in the other dimension. All right, so this thing really worked. Like it actually worked incredibly well. It learned to walk in about a minute. I'll show you the videos, but that meant that in the first couple stops it would run out of energy and stand still. But within a minute, it stabilized the nominal limit cycle, and then I started walking it around, and it would always converge. So the parameters would converge if the world was stationary in about 20 minutes. The value function made a big difference. So if I reset only the policy, but not the value estimate, that it would converge instead of 20 minutes in 1 or 2 minutes. So that made a big difference. Okay? And the learning was quick enough that the robot would constantly adapt to the terrain as it walked. Once the initial learning from a blank slate took some time, but the experience was that once it learned any walking, if the world changed, it could adapt very, very fast. Okay? So the return map of the system with the controller, with the zero controller, was that it would constantly run out of energy and stand still. Okay, but then after learning, it had this nice return map like this. It would still get stuck at the bottom, but then it was trying to approximate that straight line, and couldn't quite because of actuator limits and probably representational issues of my limits of my policy, but it worked pretty well. Okay, so this was my life back in the day. The initial versions had foam pads because it fell down sometimes, even though it was supposed to be able to. And because I was punching to get it started before it had this little kick it to give itself a random initial condition. This was the sort of didn't hit anything. And then you'd start walking it around, okay, and it would stumble in the first few steps. Then it would stabilize the new limit cycle and learn a policy that was more robust.
You're telling it to do that, right?
I told it to walk really fast to see how it would handle it.
Their perturbation experiments to stabilize, in the name of science, of course. Right? Okay, this is part of it. And then it would walk off down the hall.
Now, would you be so kind?
I know that's probably not turning off their volume, but okay. And I don't know, this thing really worked. I used to take it on all my, my trips. I would take it to conferences. It would walk around, no matter what surfaces it would walk on. It would walk from one to the other. One day, I remember giving a talk, and it was kind of walking funny, and I thought, something's wrong. This was it walking towards the media lab from E25. But it turns out in the airplane, the ankle, the universal joint in the ankle actually broke. It just snapped, and it had learned to limp, and it still walked. Right? It wasn't as graceful as it was before, but it really, really worked well. With a level of robustness that maybe I haven't achieved since.
How much of the robustness do you think comes from the simple controller and learning method versus careful design of the actual mechanical system?
I think that dynamics? Yeah, I think they're hand in hand. I mean, they're deeply coupled. I think that this was a robot that was tuned up to learn, right? The learning couldn't do damaging things to it. It didn't have much to learn in order to perform well, and it didn't have to adapt very much when the environment changed, right? It was built to be simple and fast for learning. Right, so there one really, really cool thing that I still think is an important lesson for myself here, but I didn't know how big the policy perturbations would have to be in order to estimate the policy gradient, right? There was a big question, would be, do you have to do some big experiment so that learning, you could tell it was in learning mode or it was not in learning mode. But the noise, the policy perturbations were extremely small, to the point where I just left them on all the time. It was not like there was a learning mode and there was a learning off mode. You wouldn't think it was trying to learn. It was just doing very subtle experiments in the policy parameters all the time, but that was enough to estimate the policy gradient. I'm sorry, this is impossible for you to track. Right? The other thing that was surprising was that the fastest learning came from a trivially low dimensional, or one-dimensional approximation of the value function. That was enough to drive down the cost, the learning rate, but and the value function could be trained almost instantly. Okay. And the delayed reward problem was more benign than I expected. I think that the robot was able to recover in 1 or 2 steps often, and that worked well even with, so I could get away with a pretty heavily discounted cost function. It didn't have to do really complex multi-step, multi-footstep recovery. Recovering over the step, over 1 or 2 cycles was enough. So that was sort of a blast from the past, right? But it really worked well, and that is a case where writing the model at the time was very hard for me. Getting those curve feed right and the impact dynamics right on the curve feed, and the rolling friction was pretty significant part of the dynamics. Those things were, I think our tools are better now. That wouldn't be too hard to write now, but the policy, a simple policy worked well, and that controller worked as robustly as any model-based thing, probably still. Okay, any questions about my, yeah? So
you have human children.
I do.
How is teaching a robot toddler to walk different than a human toddler?
My kid was actually just learning to walk when that happened, and so there were, the reporters used to, there was a. In fact, so I had one time when there was this film crew shooting it, and there was a toddler that they brought in to because they thought it'd be a cute picture or whatever. And well, here's one thing I learned instantly: the toddler always wins, right? So the kid, this was not my kid actually, it was a photographer's kid, looks at my robot, walks over, pulled the power plug in the robot. It took about 12 seconds for it to disarm my robot. So this is faster, right? But it's such a tuned-in little simple case, right? in all of the reinforcement learning, I put up maybe reinforcement learning as a theory of general intelligence. I think the biggest argument against that, the thing that reinforcement learning can't explain, is humans' ability to learn from a few examples where, right now all our reinforcement learning, even when it works brilliantly well, typically takes many, many, many trials, millions of trials. So somehow there's a gap in what reinforcement learning can do compared to what humans can do. Those are roundabout answers to the question, but yeah, I hear you. Did you have
an idea going in of what the convexity of the policy you're taking gradient looks like?
It was a linearly parameterized policy. So all of the non-convexity came from the robot dynamics, which I never modeled. I didn't model explicitly for that.
So did you have any idea whether you know you weren't going to get stuck in open and going in there?
I did lots of experiments to see if it would converge to the same policy experimentally, and in controlled conditions, it tended to find the same weights. So there was post hoc evidence that there was some sort of convexity in that landscape. Those weights moved, so once it was changing environments, I don't know, but in the simplest case, it did seem to be converging to a common set of weights.
How did you incorporate exploration into your policies? And also, how did you make sure, since you're using a real robot, that it can convert itself while exploring?
The robot was designed to be benign, so that it wouldn't. Okay, we did have it sometimes go over, and
yeah.
So the first experiment that really worked well, which was the initial conception of the idea, was that we'd walk downhill passively and then just slowly lower the ramp, and it would sort of never have to deviate very much from the limit cycle and just learn and walk. But the learning worked well enough that now I could start from the ground and still learn to walk. Going uphill and other things where you're more on the verge of near the region of attraction, and you could potentially go over, those were much more dangerous experiments, if you will. The learning, how much exploration, that exploration came from the noise that I added to the policy parameters, and like I said, I was surprised that small amounts of exploration were enough to estimate pretty big changes in the policy gradient. Yeah?
What lessons did you learn from this that might apply, or how it might be not applied to a robot like Atlas?
I don't think reinforcement learning has yet demonstrated something that I'd be willing to run on Atlas. But that's important. That's something that we should be working on. People talk about safe reinforcement learning. It's hard to do that completely model-free, right? But those are important big questions, and I think that'll be So AlphaGo, I think, was extremely robust, right? Human players could push it, and it was still robust. It's not clear that it's hard to know when the videos we've seen of reinforcement learning results on robots, but they don't seem to have the same levels of robustness yet. We're even trying to use, deep networks to approximate the optimal cost to go that we can get from mixed integer optimization to run on Atlas, and it's very hard to come up with a network that you'd be willing to run on the robot, right? We're playing all kinds of games to try to use the two, and we have some work even on trying to do verification for deep neural networks because these are important questions. Okay, so that's one answer to the question. What lessons? I really do think online adaptation is important. I really do think that these algorithms are best in class when you don't have good models. But I also really think that when you do have a model, when F equals MA is easy to write down, then you're going to do a lot better if you can exploit the structure of that model. So almost always, even if you're doing brute force policy, if you're doing policy search, but take the gradients through the plant if you got them. You don't have to do trial and error and millions of trials. You can just do direct optimization. I still think direct optimization on policies of complex robots is a non-convex, hope for the best operation. And in some cases, that's the best we have right now. In other cases, we try to do better. And that's actually a nice way to sort of go backwards in the course, right? I hope that you've seen the progression from the very simple systems from Pendula and Acrobat, where we had pretty powerful methods. We were able to find convexity in many cases, find sums of squares or whatever it was, put pretty powerful optimization tools that we were able to expect them to converge when it worked, right? We gave up a little bit more when the systems got complicated. We started doing trajectory optimization, which is a non-convex optimization, instead of the convex optimization in the lower dimensional systems. We gave up even more to something like that stopped working when we got to the motion planning problems, where the geometric non-convexity was so severe that local minima were just everywhere. So you have to give up more and you do motion planning. Okay, and then we gave up even more when we got to systems where we didn't have the model, and then we had to do reinforcement learning type ideas. Okay, but I think those were carefully, the order of the class was carefully architected to try to introduce those methods where we used our best methods as long as we could and only introduced a new algorithm when we needed to because the problem got hard in a way that we couldn't address. So I hope if that you look back and you see that lineage, and that helps you pick your algorithm when you've got a system that you're trying to control going forward. Any other questions like that? Those are really important questions. Cool, okay, well, I'm done. Your turn next week. I'm really excited to see what you guys have been doing, and actually it's just really fun. Like watching all the things that work is a very, very good way for you guys to get a sense of what really works and what doesn't work. Like, yeah, you get a lot of intuition about where the algorithms pay off when you just watch lots of people having tried lots of things with their common vocabulary. So please come to everybody's presentations, and they're going to be great. They're not going to be online, so if you're watching from home, you got to come in next time, because we don't want to have you all sign release forms or whatever. So you got to come here to see the talks next week.